All right, guys. Hey, this is our practice test answers for our phase change and pressure unit. And the first question here has on measured the temperature of the pond near his house. Before he left school, the water at the pond was 18 degrees Celsius. When he came home from school, the temperature of the pond was higher than it was in the morning. What happened to the water molecules while at school? Well, there's a couple of important things. One I forgot to highlight here. One is that the initial temperature was 18 degrees, which is above freezing. So the water was a liquid. And then it says the temperature went up throughout the day. So energy was added. It doesn't tell us what its final temperature is, but I think we can pretty much assume it didn't go above 100 because nobody's ever seen a pond boil away. And so we have to ask ourselves, well, what do molecules do under that situation? And the correct answer is the molecules start moving faster and move further apart. And one of the ways, let's look at a couple of the wrong answers on here. A says the molecules got closer together and move faster. Well, one of these things happens when you take energy away close together, and one happens when you make them go heat it up or add energy. So this one's got a contradictory statement. This one says it went from zero freedom to freedom, which means it went from being frozen water to liquid water, which it didn't do. We were above 18. And then the final one says the molecules became larger. Well, it definitely wasn't that one because the molecules don't change their size or the particles don't change their size. They just change their distance from each other. Okay. Second question is almost the same question, but you have an airplane fuel tank here that was at 27 degrees Celsius, and it says that we took energy out. We decreased its temperature. So this is just like the opposite of the last question. What's going to happen if we decrease the temperature? Well, here it is. The molecules started moving slower and they got closer together. We know that when we take away energy, we slow particles down and that makes them go close together. Again, look at the incorrect answers. The molecules got further apart and had total freedom. This means it turned into a gas. That wouldn't happen when we cool it off. The C says the molecules lost all freedom. That means they turned to a solid. That hopefully didn't happen in the airplane. And D says the molecules became smaller in size as they got colder. Once again, the particles don't change their size, they change their spacing and their speed. So that one can't be correct on that. Okay, moving on to question number 7. So this one's got a lot of wording and you got to really keep track of it. Hopefully everybody recognized I couldn't change this on the test because this is the GIF, but attraction means cohesion. So this sweet food has weak cohesion. The sour food has strong cohesion. So this says a cook had a jar containing sweet food and a jar containing sour food. The image above shows the sweet and sour foods at room temperature. Both foods are liquid. That's a really important thing. It tells us the state at the start. Then it says we added energy, we transferred into it. So both ones got, and it says the same amount. So both got the same amount hotter. But later it says only one of the foods changed phase while the same amount of energy was added. Which food changed phase and how did it change? Well, first of all, it started as a liquid. If we add energy, there's only one way you're going to change phase, and that is you're going to go from a liquid to a gas. You're not going to change phase into a solid when you're adding energy. The other thing we know is only one did that. So we need to think about which one of these is the easier to make change phase. And we saw this when we did our alcohol and water demonstration. Alcohol changed phase and turned to a gas in class when the water didn't because the alcohol's cohesion was lower, which means its molecules don't want to stick together as greatly, which means it changes phase at lower temperature. It's easier to melt. It's easier to change into a gas. So right from that, we know that this one has got to be the one that changed into the gas while this one remained a liquid because its stronger cohesion prevented it from doing that. Again, really kind of the same thing we did with the alcohol and water in class. So if we look at our answers here, again, we'll look at our possibilities. Notice we should be able to throw out C and D because C and D says the sour food changed because of weak cohesion. But it says in the picture that the sour food actually has our strong cohesion. So that can't be correct. Okay. And we know that the sour food didn't change. So we can toss out D and C and D. So it's either between A and B, and A is correct. Says the sweet food changed because the molecules were able to move fast enough to overcome the cohesion. Its molecules now move further away from each other with total freedom. That total freedom describes being turned into a gas. Look at B. The sweet food changed because the strong cohesion between the molecules made their movement slower. Its molecules now move around each other with some freedom. Well, we got a couple problems with this. One, it said it made that adding energy made their molecules move slower. That doesn't happen. And the other one is it said its molecules now move with some freedom, which means it's still a liquid. And it says it changed, and we talked earlier about has to be a gas. So this one's more complicated, but this is really just about cohesion, and this is about our alcohol and water thing we did in class. Okay. Question 4 gets considerably easier, I hope. It said Jamal's bicycle is made of aluminum. When are the aluminum molecules in the bicycle moving? Really, I hope you could have answered this before we even did this unit, because we know that it's got to be C, they're always moving, because if there's a point where they're not always moving, that means we're at absolute zero, and we are never at absolute zero. So 5. When does gas apply a force? When a particle strikes the surface. We did our thing with boxes where we shook the boxes with the ping pong balls in them. The higher pressure were always the boxes that made more noise, and they made more noise because the particles struck the surface more often. We talked about the noisier ones were the higher pressure. So you actually get a force when the gas hits the surface, and that's because of Newton's second law. You have a moving mass that's accelerating when it hits a surface. That applies a force. Number 6, what kind of force does gas never exert? Well, think of this. We just said when it strikes a surface. Well, when you strike a surface, you're never going to make a pulling force. Gas pressure is always going to be a pushing force. And finally, these are really crucial also in our drawings. It says, tell 3 ways we could reduce the pressure of a gas. In other words, to make them hit the surface less often. 1 would be make a bigger volume. When we put the ping pong balls in the bigger box, they didn't make as much noise because they had to travel further before they hit the side, and the hitting the side is when we get the pressure. We also could cool or lower the temp. If you slow the particles down, they're not going to apply as much pressure because they won't hit the sides as often. When we did boxes, we modeled high temp by shaking the boxes really fast, which made the particles move really fast. They made a lot of noise, a lot of pressure. If you do it really slowly, like a slower moving particle, it's going to hit it less often, lower pressure. And then finally, we can simply remove mass. Again, I'm going to go to our boxes demonstration. When we had more ping pong balls in the boxes, they made a lot more noise. They hit the sides of the box a lot more often. They had higher pressure. When we removed those ping pong balls and shook the box, less noise because they hit less often because there were fewer of them in there. And that also lowered the pressure. So 3 ways we can lower pressure, bigger volume, lower temp, or removing mass. And we saw this across the board in a number of things. Our final ones are worth a pile of points, guys. We've been doing these in class, and actually some of these are directly out of your notes. It says for the next 3 questions, draw a model of the situation described. Label your model where the high and low pressure are. Also exclude arrows to show the direction of the air pressure force, and then write a short description telling how the high and low pressure was created. So the first one is the syringe when we push it in and it's covered. So here's that picture, and you need to have all these things. Here would be high pressure on the inside, and we have force arrows. This is why when we let go of the plunger, when we pushed it in, it actually came out because the force was pushing it out. And we know the cardinal rule of pressure is that high always wants to flow to low, and the high pressure inside the syringe wants to push to the low pressure outside the syringe. And we also want to tell how that pressure was increased Well, the pressure was increased by reducing the volume in the syringe. We put the air in a smaller space, hits the edges more often, increases pressure. So you'll be scored on the arrows, the high and the low pressure, and your explanation. These are worth a lot of points. Moving on to the next one. The crush can as it was being heated. Well, this one draws out like this. Pardon me, excuse me. The pressure inside the can increased by heating the particles and making them move faster. And the high pressure is inside the can. It's flowing to the low pressure outside the can. We're showing the force arrow of the high pressure moving to the low. And one of the giveaways of where the high pressure is that the steam was coming out of the can when we were heating it. And that means that the high pressure only flows to low. Just by looking at the direction of the steam, we should get that the high pressure is inside the can. And this is why it was being heated. Now, when we flip this over later to where the open end is in the cold water, that was a different situation. But under heating, the high pressure is right here. And again, label the high and low pressure. We'll have a force arrow correctly showing the direction of force, high pressure going to low pressure, and then an explanation of how we got that high pressure. Okay, last one. The vacuum chamber when it was empty and no one could pull it apart. Well, this one, guys, would look like this. By taking mass out of the container, which is what the vacuum pump does, we ended up with really low pressure inside the container, and the high pressure in the room, cardinal rule of air pressure, it wants to get to that low pressure. And it was pushing on all sides of the container trying to get in there. And when the people in class were trying to pull this apart, they were trying to overpower the air pressure in the room, which they had no chance of doing. So once again, high pressure labeled, low pressure labeled, the direction of force labeled, and telling how we got the low pressure. Here we got the low pressure when the mass was removed. You're going to really want to review your notes and all the models in your notes because they are going to be very, very helpful on this test. And that's it for our practice test. Thanks for watching.